Good evening, everyone. And on behalf of the faculty and students of Shaheed Rajguru College, I welcome you all to the first ever webinar hosted by our department. Um, I'm extremely sorry for the initial technical glitches that we had to face. In spite of all the mock and trial meetings that we held for the past 2 days, still we had to face it. So that proves that uncertainty can come anytime, and this pandemic situation that has come up has taught us many things. It has in fact connected the whole world in a different manner. So like as Archie has already introduced Professor Manu Kaur, it gives me immense pleasure, and it's a matter of pride for me, especially because we have studied together. So we did our masters at MPhil together, and it's a pride to see my own friend, delivering a lecture through this platform, which otherwise I would not have even imagined. Because when she visits India, it becomes at times difficult to, find a common time when students are also free. She's also here, and then we could have hosted a lecture like this. So the only silver lining in this grim situation is this only, that we are able to listen to somebody who is so far off, sitting at our homes, not even in a classroom on wooden benches. We are comfortably sitting on our chairs and listening to her. So as introduced, she would be talking on clock arithmetic and secure communications, which is her strong forte, her field of expertise, and the need of the hour also. So it'll be great for us, and especially with the world changing, the normal norms being redefined, we have to resort to online teaching, online communications, online transactions more than what we had been doing so far. So in this era, security is a major issue. So her topic that she has chosen for today's talk is very apt and relevant in today's situation. So I would now request Professor Manu Kaur to please take over and start her talk. Thank you so much once again for joining us.
Thank you so much for the lovely introduction. I'm very happy to join all of you. As Dr. Vinita mentioned, I studied at the University of Delhi, so I have a very soft corner for Delhi University. And it's always a pleasure to be able to connect with your students. Are you going to make me the host so I can share the presentation?
No, I think you can share your screen like that only.
Okay.
We'll disable other screens.
Okay, perfect.
Okay.
And also, how much time do we have?
Take as much as you can. We are at our homes, comfort. You have started your morning. We are ending the day. No problem.
Okay. I will definitely try to make it very less mathematical because I know it's evening, and so I'm hoping to just tell you a few stories. So that's what I'm going to try to do.
Okay.
All right. So thank you everybody for joining. We will talk today about clock arithmetic and secure communications. So just a little bit about my experiences here. As you can see, I went to LSR, and then I went to Hindu College, and went to the University of Delhi for my PhD, my MPhil. And then I came here to Urbana-Champaign. I'm quite active with the American Math Society and the Math Association of America. And I will be representing the US at the International Congress in Math Education. This was supposed to be this summer, but then because of the pandemic, it's postponed to next summer. Okay, so what is the setup? So everybody remember Alice in Wonderland and Bob the builder, right? So Alice wants to send a secret message to Bob, and Eve is eavesdropping, and Eve is evil, and Eve is smart. And the question is, how can Alice send the message to Bob? So who cares for secure communications? Of course, all of us now, right? But even from the 17th century BC onwards, the oldest known method of encryption is the Greek Sicily, in which Spartans, what they did is they took a rod and they wrapped paper around it, as shown in the picture, and they wrote the message across like this. So they wrote across the paper like this, and then they'll open the paper and send it off through a messenger. And so this is the oldest method of the encryption. And so here's an example. Say, for example, the message is, "Help me, I'm under attack." So when the person opens it, the alphabet is written in a different manner. Now what the messenger can see is something like HENT. So what they can see is the vertical orientation, and they're not able to read the message. So what would Bob do? What would the other person who wants to decrypt the message, how would they decrypt it? Any thoughts about that? So I think it'll be nice. I have another computer open. And so if you wanted to answer my questions in a chat, I'm happy. I'm looking at your answers here. So my question is, how would Bob decrypt? Any thoughts about that? Okay, we'll let you warm up a little bit, and then maybe later you can start texting a little bit more. But what Bob can do is wrap the parchment around the citily, around the rod one more time. Yes, exactly. They would read horizontally. They would put it back on a rod, and then they start reading horizontally. Now I want you to think about what would happen if the bad guy, Eve, she intercepts the message, which is like this mixed up rod, a sentence like this vertical form. What would they do? What could Eve do? Would she make up different rods of different diameters and then wrap it around them and see if she can read the sentence, or can she do anything better than that? So any thoughts? So Eve can, one option for Eve is to come up with a, because she would know how, she needs to know how many letters come across the diameter of the rod, right? Like if the rod is very thick, then it's fewer words will come around on it. And if it is very thin, then, if it's very thick, more words will come around it. If it's thin, then very little, few words will come around it. So one way is that she can just construct different rods, different diameters. Or the other option, that's where math comes in, is she could say, well, that the diameter is such that 4 alphabets can come in. And so I'm going to put them in a column of 4 rows each, like that. And that will help her understand it. So she could make a guess. She could say, okay, 4, or maybe 4 doesn't work out, then she could try 5. So, but with a few choices, she could figure out the message. Here's another very old cipher, the Caesar cipher. The Roman Emperor Julius Caesar used to use it. And what he used to do is he used to just like shift the alphabet 3 units to the right. So for example, A gets encrypted as B, B gets encrypted as E, C gets encrypted as F, and so on. So if your message is the quick brown fox jumps over the lazy dog, then I have ciphertext in front of you. Now, one thing you could do is you could look for just type ciphertext and this wheel will come up. And what you can do is you can make a wheel, like one circle of ciphertext and another circle of plain text, and you could move it 3 units like that. And then you will have the plain text and ciphertext aligned to each other and you read your message. So that's one thing you could do as a little pastime at home. But then there is a computer program. It's called The Black Chamber by Simon Singh. Check that out. It's very fun. And you can just type in your message and say shifted by 3 and it'll encrypt it and then it can decrypt it. So here's a little homework for you. And so the question that I have here for you is, how can Caesar cipher be implemented in a computer? So if you want a computer to do this for you, do this encryption of moving 3 units to the right, how would you have a computer do it? So that brings me to the idea of clock arithmetic. Yes, I have a comment here that says, is the key 3 here? Yes, absolutely, the key is 3 here. So you're shifting by 3. So how can a computer do something? Computer, you have to represent everything by numbers, right? So English alphabet, just for fun, we could say, okay, A is 00, B is 01, and Z is 25. We're encrypting A as D, so 00 gets encrypted as 03, 01 gets encrypted as 04. So essentially what we're doing is you're adding a 3 every time. And yeah, I see some of you already know modular arithmetic, and that's exactly what clock arithmetic is. So what happens is when you are at 23, you add 3 to it, you get 26, but 26 is none of A through Z. And so what you have to do is you have to bring it back to A. And similarly, 24 plus 3 is 27, but you bring it back to 1. And 25 will become 28, which again, you'll bring it back to C. So this exactly is the idea of clock arithmetic. Clock arithmetic is arithmetic modulo 12. So after 12 o'clock, the next hour, instead of saying 13, you say 1. The next hour, instead of 14, you say 2. So essentially what you're doing is A is equal to B mod K if K divides B minus A. Now I'd like you to write this down on the side because we're going to use this later. So just write down this blue part. A is equal to B mod K if K divides B minus A. Usually we write equivalence and not equal to, but Gauss said that modular arithmetic basically behaves, this equivalent signs just behaves like equal to. So for example, if you have A equivalent to B and C equivalent to D, then you can multiply both sides. You can say AC is equivalent to BD, and so on and so forth. It pretty much, even though division is involved, pretty much behaves like equal to. All right, so please put this blue thing down on the side. And in the Caesar's encryption, what you're doing is you're starting with X, you're adding N, but then you're dividing by 26 and writing down the remainder. So that is what your encryption function is. And the decryption is DNX is you subtract N. So in Caesar cipher, N is 3, so there's no reason to do 3, right? Caesar used to do 3, but then we could do any rotation. So N could be 0 to 25. And we call this a shift cipher because what you're doing is you're shifting the alphabet. And in this example, N is the key of that shift cipher. All right, excellent. So let's move on. What can Eve do? If Eve wants to, Eve encrypts this message, Eve gets the message on the way, the encrypted message. Can Eve decipher it? So one thing that Eve could do is brute force, which is just try all possible shifts and there are 25 possibilities. So excellent. I see a lot of people are thinking ahead of me here. So, you know, for example, if the message was EXXEGOE, like that, just shift it all the possibilities, and then, you know, you can see that when the key is 4, you get attacked once. So that's your message, right? That's one way of doing it. But the other way, which is a smarter way, is the frequency analysis, which we know that in the English alphabet, E is the most frequent letter, and T is the next frequent letter. And so that obviously is a much smarter way of doing it, right? So you can try all possible shifts if you have a lot of time on you, but otherwise be smart and see, look for the most frequent alphabet and see if E fits there, right? Actually, we know the English letter frequency. This is based on a sample of 40,000 words. And you can see that E is 21,912 and so on and so forth. So you can see that E is the most frequent, and T is very frequent too. T is 16,000. A is the next frequent. So you know that E, T, A, O, I, these are very frequent alphabet, and we can always exploit that. In fact, the frequency analysis was discovered many, many years ago in Iraq. And here's a transcript, a manuscript from Al-Kindi, where he is describing exactly the frequency analysis. All right. There's also a fun story. I promised you I was going to give you stories. So Mary, the Queen of Scots in the 16th century, was conspiring against the British monarchy. And she and her co-conspirators, they decided they're going to write this symbol for A, this symbol for B, this symbol for C, and so on. They also decided every time they have to write and, they'll say 2. Every time they have to write 4, they will say 3. And so they have this little key here, and this is a substitution cipher. And they used it to encrypt messages to each other as they were conspiring against the British Queen. And Mary wanted to assassinate Queen Elizabeth I, and the co-conspirator was Anthony Bington. But then, frequency analysis had been discovered, and so Mary was found guilty and executed, and the Queen was saved. So frequency analysis has been used across the centuries. So I have a fun activity for you. And probably more fun doing it in person, but then let's try it. Let's see how it goes. So this is based on Sherlock Holmes' mystery story, The Mystery of the Dancing Men. You guys should read it. That book is a fun read. And so here's the story. So there's this person, his name is Hilton Cubitt. He lives in Elridges. And he shares with you a paper with the following mysterious sequence of stick figures. He found that in his garden. Okay, so let me draw here a little bit. Okay, so he gets this sequence of stick figures, and he's really, everything in his life was good until he, okay, hold on. Well, when I can draw, it seems like I can't move the thing forward. So let's move on, and then I'll draw later. Okay. So somehow I I'm not able to move my slide forward anymore. Okay, so it's working. So Hilton Cubitt of Eldridge's has shared with you this paper. So you are the detective. And this paper has a bunch of stick figures. And he recently married a Chicago woman named Elsie Patricks. You know, so you're asking, well, could you please, somebody has been writing on my slide, so please don't do that. So he recently married a Chicago woman named Elsie Patrick. And it was a happy marriage until the stick figures started to appear. And so you're in charge. So you call your friend in the Chicago Police Department and ask about Elsie Patrick. And you learned that Elsie was the daughter of a Chicago crime boss and was engaged to Abe Slaney, who worked for her dad. And Elsie had fled to escape her old life. So Hilton Cubitt tells you that when they got married, Elsie had told him that she had a difficult past, and he had promised he was never going to ask her about her past. That was just an understanding they had between them. But now that these stick figures have started appearing, he sees that Elsie is stressed out all the time, and he knows that he needs help, and so they have come to you now. So Hilton Cubitt has given you this information, and you found some further from your friend at the Chicago Police Department. But subsequently, there are other messages that appeared. So there was this one message that I shared with you earlier, but then there are more messages that kept coming, and there was this message 4 in a different handwriting, and your task is to figure out what is going on here. So what could you do? So one thing that that Hilton Cubitt's message, the first message, one thing that you notice is that there are some flags at the end of some pictures. So you say, well, what does that flag might mean? So any thoughts about what that flag could be? Maybe a period. Yeah, that would be an option. Any other thoughts? So there are these flags, right? Right, you see the flags. So maybe they are the space, yeah. Maybe they are the space. Maybe they are the end of a word, right? Yeah, it looks like message 1 and 2 are the same. What is the most frequent message? What is the most frequent symbol here? Do you see which one is the most frequent symbol here? So the most frequent symbol here is this one, isn't it? The fourth one in first row. Yes, the fourth one. This one seems like the most frequent symbol. So what do you think this one is? Hopefully that represents E. Excellent, right? So you know, but then this last message over, the message number 4 is just a 5-letter word with E in the second and the fourth place. So think of 5-letter words with E in the second and the fourth place. Can you think of some 5-letter words that could have E in the second and the fourth place? Like fever, right? Never. Any other you could think of? 7, very good. Reset. Fewer. Right. So we could think of all the 5-letter words with E in the second and the fourth place, and we have a great start here, right? So, and then once you know that, you can go back and put all the E's in these messages wherever the E's appear. And then if you think, since this message is in a different handwriting, you try to say, hey, which one would make more sense, right? Maybe never would make sense. So you can think of this one as E, this one as N, V, E, R. So now you know N and V and R, you could place those symbols and then go from there. It's like a little puzzle that you can then solve. So to save time, actually in the mystery also, this is exactly what they do. Sherlock Holmes figured this out. He starts with E and then he goes backwards and he deciphers the message. So I won't annotate again, because once I annotate, it just takes me to, and my annotation passed on to the next slide. So give me a second, I have to erase. Oh gosh, okay, give me a second here. So I want to erase this now. Okay, so I will move on. I won't annotate next time. Okay, so by doing this, if you think of the first, the fourth message to be never, then you can start filling out the other ones. So message 3 had 2 words. You already know the E, and so you can start thinking about what it could be. And then message 2 was 2 letters and then another 7 letters. And once you already have the E's, you kind of make a guess. Well, it might be Eldridge's because that's in the problem, in the given information, and so on. So you can see that by substitution, frequency analysis, you can actually come to the answer. So the message, you can see now all the messages. In fact, they get one more message, the last one. It says, Elsie, prepare to meet thy God. And then Sherlock Holmes knows that she's in trouble, so he runs. But then by then she's already dead, and the police is thinking it's a murder suicide. Her husband was shot and Elsie was shot. And but Sherlock Holmes knows that it's not murder suicide, that there's Abe Slaney who was in charge of this, who was doing all of this. All right, So here's another example where you could do substitution cipher. But in this case, we don't have a simple shift. What you have is some kind of a shift. So what I did here is I took that message, I put it in Simon Singh's black chamber, and I saw that G comes 8 times, V comes 15 times, Z comes 8 times, and so on. So I know that V probably is 15, and when I put that in, I get this kind of message. And you can make good guesses. So for example, the first one is T blank. And then you think of, hey, what are the possible words that are 2 letters and start with a T? Not too many, right? Maybe this one is T-O. So then you know the next symbol is O, and you keep going from there. So play around with Simon Singh's website. It's a fun place to be. And this is the message. To prove the importance of secure ciphers, here's the tragic story of Mary, Queen of Scots, who was foolish enough to use the weak cipher long after code breakers had mastered frequency analysis. So that's the same story here. Okay, so who cares about secure communications in the current day? Well, defense systems, e-banking, e-commerce, everything, right? You buy something at Amazon.com, you can deposit checks in your bank, you can, we always use online course management systems. And now I'm sure all you guys are using online to teach. So it's very useful. Everybody wants to be secure. Professors want students' papers to be secure. The grades to be secured, and so on and so forth. When you use a cell phone, you hope that whoever receives the signal transmission cannot receive your message that you are giving. So anybody who wants to securely transfer information, which basically means all of us, everybody, we care about secure communications, right? So let's talk about Alice and Bob one more time. So Alice wants to send a secret message to Bob. And in so far what we've done is we know that these two are there, right? Alice wants to send a secret message to Bob, and Eve is watching, Eve is evil, Eve is smart. But then Kirchhoff said that if you really want to make a secure public system, encryption system, then you should assume that the method of encryption is public knowledge. In the previous examples that I gave you, it was important to keep that method private. It was a secret between the two people, between Alice and Bob. But Kirchhoff around early 1900s said, well, that's not going to work out. You have to assume that everybody knows the method. And so the security depends on the key. So when you do substitution cipher or when you do a shift cipher, there are only 25 keys because there's only 26 alphabet. And you can break it by brute force very easy, right? So the key is important. The key needs to be secret. That's what Kirchhoff said. But then in the modern day scenario, what happens? You want to send your credit card information to Amazon.com, and it's all happening through the insecure internet, right? We all know internet is not very secure. It can easily be hacked, right? And evil Eve, those people who want your credit card information, who want to steal your identity, are listening. So how can you send your information, your credit card information to Amazon.com through that insecure internet? The big problem over here is that you and Amazon never ever meet in person, right? You never meet in person to exchange a key. See, normally, like in the previous example, in the private key crypto system, you could write something, you could you could put a secret in a box, and then Alice puts the secret in the box, locks the box with her key, sends it to Bob. Bob has the same key, and so he can open it. So what they have done is they have a common key. That's why it's called the private key crypto system. So you have a key which is private between you and Bob, or you and Amazon.com. But in our situation, in the real life situation, you never get to meet Amazon.com. Everything happens over the insecure internet. So this is the big question. How can that be done, right? And this was done in 1970s, and this is what has revolutionized communication. So now we all use email and banks and all of that stuff, shopping and stuff. So the big deal here is that Alice and Bob cannot meet in person to decide the method or to exchange the key. So that's the problem that public key cryptography solves. So here's the key concept. The key concept is one-way function, something that's easy to do and hard to undo. So again, I would like you to think about things that are easy to do and hard to undo. One example is multiplication is easy. So it's easy to multiply numbers, and factoring is very hard because, say, if I give you 5,023, then you have to check whether it's divisible by 2, is it divisible by 3, is it divisible by 4 or 5, or at least all the prime numbers before that number. So that is hard. So square a number is easy, taking square root is hard. Excellent. Any other thoughts? So think about things that are easy to do and hard to undo. So that's our one-way function. Any other thoughts? So I have one chat comment here: square a number and take a square root. Adding weight and losing weight. Breaking a plate and putting it back. Yes. Learning the notes, that's easy. And writing in exams is hard. I don't get that one. Wasting the semester and then, Okay. All right. So what this public key cryptography is based on is on a very simple idea that multiplication is easy and factoring is hard. All right, and there's another one that's based on modular exponentiation is easy and discrete log is hard, but I won't talk about that. So again, Alice wants to send, so here's Alice. She wants to send the message to Bob, but for that she needs to encrypt it. So she encrypts it to a function f. But when Eve gets that function f, the encrypted function, Eve should not be able to get the x back. So that's why we need a one-way function. And on the other hand, Amazon.com should be able to decrypt. So this going backwards, or the inverse of that function, should be easy if there is some additional information, some extra information. We call that the trapdoor. So what Alice does, so here's the idea. Alice uses, so Bob puts out a key. Bob puts out a key on their website. So Amazon.com website has a key, for example. Everybody has it. Everybody can take it. And then Alice uses Bob's private key, public key, Bob's public key, which is on the website, and encodes her credit card information with that, and then sends it across Eve can see it, but Eve only can see f of x. So Eve cannot do the x back from there. But on the other hand, Amazon.com has this private key, which is a secret that Amazon.com does not share with the world. And they can use this trapdoor information to get the credit. So this is the big idea of public key encryption. So how can you do this? So RSA crypto system was invented in 1977 by Rivest, Shamir, and Edelman at the Massachusetts Institute of Technology. It's based on the fact that multiplication is easy, but factoring large numbers is hard. And it uses a very simple construct, again, a very old construct, the Euler's pi function, which is the number of positive integers, which is less than n, that are relatively prime to n. So let's think about it just a little bit. So what does that mean? Number of positive integers less than n and relatively prime to n. So for example, if you have 3, then phi of 3 is just 1, because 2 is the only prime number that is smaller than it. Phi of 8 is 4. So you can start with 8, write down all the prime numbers that are, all the numbers that are relatively prime to 8. So 1, 2 is not relatively prime to 8. So 3, then 5, and then 7. So there are 4 numbers that are relatively prime to 8. Similarly, if you have a prime number, for example, 101, then every number before that prime number is going to be relatively prime. So when you take a prime number, phi of 101 is 100, phi of 13 is going to be 12, and so on. And it turns out that phi is a homomorphism, for those of you who have seen that word before. Phi of PQ is P minus 1, Q minus 1. So it's very easy to find Phi of PQ if you already know P and Q. So if you know N is equal to PQ, then phi of N is going to be P minus 1, Q minus 1. But in general, phi N is hard to compute without the factorization of N. And there's a theorem, the Euler's theorem, says that if the GCD of M and N is 1, then M to the phi N is congruent to 1 mod N. So M raised to the phi N is congruent to 1 mod N. Okay, so excellent. So this is all we need. This is the only math part of my talk. Okay, so RSA crypto system, how does that work? So Alice wants to send a message to Bob. Alice is me or you, right? Bob is Amazon.com. So what Bob does is Bob chooses 2 large prime numbers, P and Q, computes N is equal to PQ. Remember, Bob only knows P and Q. Nobody else in the world knows P and Q. Bob multiplies them, that's easy, and computes N is equal to PQ, and also computes phi N. Phi N is P minus 1, Q minus 1. But Bob keeps all this red part that I have, that's Bob's secret. So Bob keeps all of that a secret. Then Bob chooses a random number E, which is such that the GCD of E and phi N is 1. All right. And then Bob sends N and E over to Alice, or you could say they just place it on their website. All right. But also Bob computes D is equal to E inverse, the inverse of E mod phi N. Since this is why we needed that condition, GCD of E phi N is 1. We wanted that condition, we wanted E to be co-prime to phi N because we wanted the inverse to exist. If this condition is not satisfied, this inverse does not exist. And so Bob cannot decrypt, okay? So that's why we need this, all right? Bob keeps that secret. And so Bob's secret decrypting key is N comma D. Again, the red part is secret. Bob doesn't share this with the world. Bob only shares N and E with the world, puts it out there. Alice uses her message M and computes M to the E mod N. Modular exponentiation is easy. And by easy, what we mean is it can be done in a reasonable amount of time on a computer. Okay, so Bob gets C, which is M to the E. And all Bob has to do is to take that encrypted message C and raise it to D. Remember, only Bob knows D, because only Bob knows phi n, because n was a secret. So phi n was a secret. So Bob could find D based on his secret. Bob has D. What Bob does is he does C to the D equals M mod N. Actually, so you might ask, how does that give him M? If he takes C and he raises it to D, how does that give him M? Well, the answer is it's just a very simple idea. It's very simple math. So could you please stop annotating my slide? Someone's been writing on my slide. Please don't do that. Okay. So D, how does that work? So D is the E inverse mod phi n. So ED is 1 plus K phi n, right? Let me explain this a little bit better. So D is E inverse. What does that mean? E times D is 1 mod phi n. And so remember I asked you to write something down. So when I say ED is equal to 1, what does that mean? That means phi n divides ED minus 1, right? And so ED minus 1 is K times phi n. And so ED is 1 plus K phi n for some K. And this is to recall just that C is M to the E mod N. And we know the Euler's theorem that M to the phi n is 1 mod N. And so Bob will compute C to the D. So C to the D is M to the E to the D, which is M to the ED, which is ED is 1 plus phi n times K. So I'll use a law of exponents. It's M times M to the phi n K. And M to the phi n was 1 by Euler's theorem. So it's M times 1 to the K. So it's M times 1, which is M. So that's how Bob recovers M. But there are many questions involved here, like are there enough large prime numbers? Is modular exponentiation easy? And we are assuming that the GCD of M and N is 1. Will that always happen? So there are a few questions here to consider. But why can't E find the decrypting key? P and Q, someone said GCD should be 1. Anyway, I'll get back to that. Why can't Eve find the decrypting key? So if P and Q are very, very large numbers, usually we use 200 digits right now. Actually, those of you who use iPhone, you can actually look in the iPhone, it is using an RSA encryption key there. So usually 200 digit long. And Eve knows N, but not P and Q, and factoring is hard. And so Eve cannot compute phi N, and so Eve cannot compute D, which is the inverse of E, and therefore Eve cannot decipher the message. But there are many other questions here. So for example, how does Alice know it is Bob who sent her the public key? For that, we need digital signatures, right? So the digital signature idea is also extremely easy. Um, both Alice and Bob pick a public RSA key and a private key, and they have a corresponding encrypting and decrypting function. And Bob wants to send, in this case, Bob wants to send that key, that public key to Alice. So Bob wants to send the message M to Alice. What Bob does is he uses his decrypting key and Alice's encrypting key and sends it over to Alice. So that's the ciphertext. And Alice uses that ciphertext, applies her decrypting key and then Bob's encrypting key. And so what Alice gets is the message M. The only person who has DA is Alice, and the only person who could have performed DBM was Bob. And so Alice can be reasonably sure that Bob sent the message. So the idea is, all of it is just based on the fact that factorization is hard and multiplication is easy. So this is just the proof of why that would be true in the other case. So it's not very hard to check. And so that's where I would end. Or actually, it's not really the end, it's the beginning, because RSA was just the beginning. There is many other crypto systems like Algomal, which uses a discrete log problem. There is, we now use elliptic curve cryptography because you can, it's much smaller numbers. There's pairing-based cryptography. We have fully homomorphic encryption, which is the background for cloud computing, which we all use these days. And so cryptography right now is more than just sending secret messages. We have to have key exchange, digital signatures, authentication. How can Alice be sure that the message is from Bob and was not corrupted by Eve on the way? How can Bob be sure that Alice received it? How can Alice make sure that Bob cannot deny having sent it? So there's a lot of questions that have to be answered for us to trust that internet exchange that we do. Zero knowledge proofs. How can Alice prove to Bob that she has a certain piece of information without revealing that information? So I have a lot of money, but I don't want to tell you how much money I have. But I want to convince you that I have a lot of money. How can that be done? So more protocols, secret sharing. How can Alice, Bob, Carol, and so on each have a piece of information that is part of a commonly held secret? So for example, defense systems. You don't want very crucial information with any one person, right? Because then the secret can get out. So usually when defense systems work with classified secrets, their people will have a little piece of that information and they're working on that little piece of information, and then it's put together, all of it. So all of these protocols are in common usage in our computer networks today. For example, the ATM, the web. And here are some helpful references. And I would like to stop here. Thank you so much. Thank you so much for listening.
I, on behalf of the department, extend a very hearty vote of thanks to the honorable delegate who took out valuable time from a busy schedule and blessed us with her presence. Ma'am, we are grateful to you for sharing with us your immense knowledge on the subject and enlightening us with your words of wisdom. I would also apologize for the inconvenience caused. We are sorry. Ma'am, the way you explain the topic is exemplary, and I hope that many of us have developed an interest towards the field after today's webinar. Also, I would like to extend a special thanks to our teachers, council members, and attendees for working towards successful organization and conduction of this event.
Well, thank you so much. It was my pleasure.
Ma'am, now I request Dr. Punita Saxena to thank Professor Manu.
Uh, Thanks a lot, Professor Manu, for your valuable thoughts. And the lecture was really interesting. I mean, yes, we all, there are a few students who are right now also studying cryptography, and they know about RSA algorithm and all. But I'm sure the others who have not studied it would definitely have developed an interest into it. And we all know that the protocols are changing day by day, and security is, everybody is working towards the secured communication and secured transactions. So hopefully in the near future, it will go on. Just before we, just leave the meeting, just one, just one thought. How do you foresee the future of education, like especially since you have seen both the countries, India as well as US, and the way we are also now at the moment, because everything was thrust upon us due to sudden lockdown and all. So we are also struggling with online teaching, learning pattern, and students are also struggling with it. So how do you see the future of education in India specifically? USA is well equipped, we all know that. You are all used to online teaching, students are also used to. So anything, you would like to motivate the students how to study with online mode?
Yeah, I think actually India is very good in terms of technology, one of the leaders in the world. But there are many courses. I would like to mention Coursera. If you do a search, many courses that are given by across the world, MIT, Harvard, UPenn, and so on. And so I know that Indian students are taking a major advantage of that. They are able, they are disciplined enough to learn through those online courses on their own. But there's something to say about a personal touch with a teacher. I think teachers will always be important. And I think India is in a position to lead the way actually in terms of designing online classes. Everybody has heard about Khan Academy, and that's an Indian person who runs it. I mentioned Simon Singh, and that's an Indian person actually. He lives in the UK, but he made it his mission to make science and math more popular. So he has a lot of fun books, the code book, Fermat's Enigma, and so on. So I think you guys are doing great in terms of online learning and teaching, and definitely can develop further on that. Yeah.
Yeah, sure. I mean, we are confident and we are sure that we'll we'll be at par with any other country for that matter. And yes, students are encouraged to take up courses through either Coursera or Udemy, whatever they find comfortable with. And I hope they use their time at home apart from their curriculum and to add on to their skills, whichever they can. So I would like to thank all the participants here who were, very interactive, also answering and giving their own opinions. And once again, thanks a lot to you, Manu, for your wonderful lecture and your time. I know you are busy. It's the end of the semester for you. You are also busy grading your students. It's a tough job. I know that. So, but then thanks a lot for taking time from your busy schedule and for being with us. So
Thank you very
thanks a
much.
lot. Thanks a lot, everyone, for joining us and making this webinar a success. And I hope in future also, because now we are used to this mode, so in future also, we'll be troubling you with your more lectures in continuation.
Sure.
Okay. Thanks a lot once again.